recording. Okay, so this is a review for units 10.1 to 10.6 for the chapter 10 test. So we had a quiz on this a couple weeks ago, but there are several new units such as the power series, binomial theorem, and the identity, the proofs. Even though we had a proof on the test, that's still coming up. But first I'm going to do a little review of the last quiz since it was so long ago. I think everyone will remember the geometric and arithmetic sequences. Essentially, we can split up the geometric and arithmetic sequence. We can have formulas and sums are the two main things that we're going to go over. And as we know, there are multiple ways to write both of these. For example, for sums, you have sigma notation. You also have just like the 1 plus 2 plus ... And for formulas, we have recursive and explicit rules. There are a number of formulas that it's actually decently important to just memorize. Some of these might seem unfamiliar, but I think you could probably figure out on the test, like the recursive formulas. Still important to know. Like here we have the geometric recursive formula, and here we have the and then for the arithmetic recursive formula, I guess I should mention this, that R and D are essentially the same, but this is common ratio and this is common difference. There are a number of ways to do the arithmetic formula. I actually like to do it this way. I drew this over there. Minus, and then minus D, because I find this just a little bit easier to deal with. I think you probably see it more often like this. Essentially, we're going back to the n-1 term, and we're using that with a common difference, essentially just multiplying the first term by 1. So these are pretty self-evident. The more difficult formulas to remember, I think, are the sums. Like we have A1 equals, S. For geometric, we have S equals A1 times 1 minus Rn all over 1 minus R, which, if Rn is essentially 0, as it will be for an infinite convergent geometric sequence, then it just simplifies to A1 over 1 minus R. This is the most important to know, I think, because you probably will be asked at some point to come up with the sum of a geometric sequence. And for an arithmetic sequence, you add up the first term, you add up to the second term, then you take the average and multiply it by the total numbers. You can also put the number on top, but I think it's more easy to read this way. In general, the types of problems we get will often have you given a certain series and required to find the formula, or it will give you a recursive formula and require you to find an explicit formula, and vice versa. So recursive formulas, as you know, require return back to the last phrase. So just as a quick reminder, if we're doing a recursive formula for a geometric sequence, for example, we would define the first term. Let's say it's 4, and we would say an is equal to an minus 1 times 3, and you have to remember to say that n is greater than or equal to 2, because with a recursive formula, you aren't allowing yourself space to go backwards because you've already defined this term. So n minus 1 is only defined, essentially, when you have at least 2. And this is going to be addition or subtraction if you're dealing with an arithmetic recursive formula. So you might be required to go back and forth between these. I think in this case it would be like 3n to the n minus 1. 4 times 3 to the n minus 1 in the explicit. Sometimes you're asked weird things like this. Like we had a question on the last quiz where you had defined a function in a series which include terms like x, x plus 1, etc. Where you have something like this where in your answer you're not necessarily including n, you do want to put in n as an element of n. So that means all your numbers are an element of all real numbers. So this is most of it for formulas. For sums, we remember that we have the sigma notation. So you say n equals, or whatever equals, and your calculators will probably be x on the bottom. Let's say it's the starting term, and then on the top is the term you're going to. So if this is 0, then it would be 5. This is 1, so it's going to be 4. And you put this in. These are pretty easy to solve in your calculator if they give you something like this and they ask you to just find it. I think this is relatively easy to do if you have one of the newer calculators where you can just plug it in. But I think a more common question is going to be giving you a partial sum and asking you to write it in this form. So for those, you might also need to use this equation. For example, to find the number of terms, like if you have using both the common ratio and the first and last term, let's say it increases like this. Well, with this, you're going to be able to tell that it's 136 terms because the common difference is 1, and the difference between the first and last, 135. And, we have this extra term. So I think this is relatively simple. So that is most of the review I wanted to go over for 9.1 to 9.3. I guess the last thing is that there will be sometimes they give you a strange series, like I don't know what to name right here. And you'll have to make equations, like let's say that this is n equals 1, 2, 3. You'll have to make equations where it's like making a system of equation with a squared, with a plus b, an squared plus bn plus c equals an, and you'll need to be able to put that into a matrix. I think that's most of what I'm going to go over for the 10.1 to 10.3, but I do also go over that more detail in the video I made for the last quiz, which is still up. One of the things that Aaron, so moving on, one of the things that Aaron said might be on the test today, or the test tomorrow, is these divisibility problems. This is a type of proof problem, so I'm going to go over briefly what notation that you want to see when describing a proof. So you have to say, let's start by saying, wait, let me get out my work for a second. So I make sure I don't make a mistake. Show that 1 is an element of n. So that says that 1 works, essentially. So if we're using this, we're going to say 6, 1 plus 4, which is 10, divided by 5, is a whole number. So 6, 1 plus 4 is divisible by 5. We're going to check that off, right? Yes. Our next step, we are going to assume x is an element of n. So for example, we're just assuming this is true. We can assume that this is true because we know that in at least one case this is true. So we're just saying that this is one of the cases that is true. So now that we have shown that one of the cases is true, we're going to try and extrapolate that to the next case and by extension to all cases by proving that x plus 1 is an element of n. So, for example, I think we haven't really gone over the reason why proving this is important, but essentially if you can prove that a certain number is an element of n, then you can prove that any number that works plus 1 is an element of n. Then you can prove that the whole set of numbers is an element of n. So you can prove that it works as a universal rule. In this case, it says true for all positive integers n, so we're actually going to want to write for positive x here. Make sure to write this. And then we're ready to start our problem. So 6x plus 4 equals 5k. K is an arbitrary value in this course, but you want to, because I'm multiplying it by 5, it will always be divisible by 5. We're going to move over the 4 to the other side. Then, because to make this into 6 to the power of x plus 1, we have to multiply both sides by 6. So, do that quickly. Then we can make this into 6x plus 1, and then distribute this out. So we're left with 30k minus 24. Now we go back to here. You see how it has the plus 4. We're going to want to add the plus 4. And then we're going to end up with 30k plus 20. And now if you do that right, you should be able to factor a 5 out of this. We can. So then we can see that 6k plus 4. It doesn't necessarily matter what's in the parentheses. As long as we can factor a 5 out of it evenly, and we can see that this is the same as 6n plus 4. So then we can say yes. And our third step, therefore, S is an element of n, and we want to write Q, E, D. So this is how you're going to do all of them. You're essentially going to move this over, move this over, move whatever over, and then multiply both sides by the number that brings this to x plus 1. For example, this is 6, here it would be 9, etc.
Also, I don't know if you need to, but for the step where you wrote 6 to the power of x plus 4 equals 5k, you can write k is an element of integers.
Yeah.
Yeah. And then at the bottom you would write, since k is an element of integers, then 6k plus 4 is also an element of integers.
Yeah, that's good to write. So you could say k is an element of integers. 6k plus 4 is an element of integers. The clearer you can be on this, with saying all this stuff, the better. I mean, really, who knows if you leave out one detail or say something wrong, if you'll really get points taken off or not. But the better communication you can do, it's just going to be better. So, going on to binomial theorem. Now, I don't know if this is common knowledge already, but there is a program you can make for your calculator to do binomial theorem for you. And because you don't need to show your work for this, then you can just essentially use the program pretty freely. But if you want to figure out how you're going to do it, well, we have, for binomial theorem, we're going to have something like ax plus by to the n. Sam, can you share the binomial theorem program?
Yeah, I'll find it. I'll put it in the thing.
Yeah, so I would advise getting that because it definitely makes these problems a lot easier. But if you're not doing it that way, you're going to have to do it with NCR, which you could explain this.
Alright, I posted it in Precalculus chat. If anyone wants to go check, they can.
Yeah. So you can explain this in any number of ways. But essentially, we're going to start with n here. So let's say we're to the 7th power. And we're going to go to 0 for the first term. And all the way up to... And then all the way up to 7. So we're going to have 8 terms. And each one we're going to multiply by ax to the 7th, and then by to the 0th, all the way to ax 0 plus by to the 7th. So, even here, I don't think you actually, you don't add them, you multiply them. That's my fault. But I can't really erase it now, so I'm just going to have to believe that's multiplication. Essentially, these will cancel out at all the more advanced levels, but let's say we have the middle term, or one of the middle terms in this case, because there are 8 terms. We're essentially going to count down, so this is 7th at 0, so at 1 it'll be 6, 2 it'll be 5, and here it'll be 4. And then we know that both the exponents are going to have to multiply, in this case, to 7. So we can do by, or they're going to have to add to 7, by to the 3rd. This is really just easier with the program, but I don't think it's also that bad to do it this way. So, whatever way, it's just kind of annoying to write out the whole thing using this. I mean, it's just a lot to do, especially if your y's aren't y, but instead like y squared, or maybe it's 1 over x. Though in those cases, it might be a little bit easier to plug it into these, and you can just immediately see. Or you could use both and check. But I'll move on to power series now. So power series, I don't know if Mr. Fisher has told all the class this, but he told our class that we are gonna have the equation for a power series for sines, cosines, and Euler's number given to us. So like these look something like this, where we have the sum of so for Euler's number, it's going to be essentially 1 plus, for e to the x, it's going to be 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. You'll have this equation. Often you'll be asked for the 4th partial sum. In that case, you're going to go all the way up to x to the 4th, but you're not going to go to the x to the 5th, because if you ask for a 5th partial sum, you're only using the first 5 terms. There are other equations like this for sine and cosine. For those, you always have to use radians. If you use degrees, you will not get a proper answer. You can check these with your calculator, but don't do them with your calculator because this is an approximation. So if you do it with your calculator, it'll be too correct. So just do this. Another part of this is let's get a power series. Does anyone remember what the page is with the power series?
It's 642 is the homework.
Alright. I'll get one of the problems on here. Oh, it's kicking me out. Here, wait, Ryan, can you read me a power series problem?
Yeah, I'll get it in a second.
Alright. Most power series problems, you're going to see something like this, and you're going to have to set it up. You're going to have to set it equal to 1 over 1 plus u, and solve for u. Ryan, I'll wait for Ryan to give a question so that it looks nice. The definition of power series is that these fractions can never be allowed to get above 1, and so they're always convergent, never divergent, because you're often trying to find the sum, and you can't do a power series with convergent.
You want me to just read it to you, or should I send you a screenshot?
You can just read it to me.
Okay. One of them is g of x equals 3 divided by 1 minus 2x.
1 minus
And
2.
then it says to find the sixth partial sum of the series and indicate the interval on which the series converges.
Alright, I can do that. So, like I mentioned, like I put up there, we're going to set this equal to 1 over 1 plus u and solve for u. So we're going to cross multiply this with this, this with this. 3 plus 3u equals 1 minus 2x. We're going to solve for u. So let's subtract 3, negative 2 minus 2x, 3u, and then u equals negative 2 minus 2x. No, this is actually 1 minus u, I think. Isn't it?
Yeah, it's 1 minus u.
Yeah, I thought I'd written something wrong. So this is going to be positive 2 over 3. And essentially when we're finding the interval on which this series converges, it's the interval under which it's going to be less than 1 and greater than negative 1. So you can, I kind of prefer to just kind of look at it because I can visualize myself what it will be 1. Since in this case, if it's greater than 3 in the numerator, we're looking for x equals 1/2, and less than 3, well, 2x is going to have to be negative 5, or less than negative 1, 2x is going to have to be negative 5, so it's going to be negative 5 over 2. Mr. Fisher said you can write the interval in a form like negative 5 over 2, 1/2, just showing the range. It's exclusive, of course, because it can't be 1. So now we have, and the power series is infinite.
Wait, Jacob, can you also write it as like x is greater than
Yes.
negative 5 over 2 and less than 1/2?
Yeah, you can write it as this too. I just prefer to write it this way. I feel like it's less work. But you can absolutely do that. Over 3 to the n. So let's see. I don't
Would
know.
it be 6? Would it be 6 instead of infinity? Because it's the sixth partial.
This is showing. This isn't solving for the sixth partial sum. This is just the thing. Yes, it would be 6. Though I don't know if there's
It's
a way
n
you can
equals
plug.
0, not n equals 1.
Oh yeah, n equals 0. I
And
don't
then
know
it'd be
if there's
5
a
at the
way
top.
that you can express this
5.
in your
5.
Oh, I should go so far back. How am I good to write that? I don't. Is there any way that you can just plug this into your calculator, or do you just have to do it manually?
You can plug it into your calculator.
No, because you have the x in it, so basically, or all you have to do is write out the 2 plus 2x over 3 to the n for the summation part. But then when you're solving it, you have to just write out 2 plus 2x over 3 to the 0, 2 plus 2x, which is just 1, and then 2 plus 2x over 3 to the 1, and then 2, 3, 4, 5.
Yeah.
But you need to like multiply it all out and solve it.
Oh, do we have to? Or do you think we're gonna have a problem where we have to actually like add the fractions?
Oh, you don't need to multiply everything out. You can just leave it in that notation. That's the way the textbook has it.
Yeah. I thought I heard Mr. Fisher said that we were gonna need to do 6 partial sum, or something like this. But I mean, it's good to know just in case. I think the more important part is probably this interval and the equation. But you would write this like, here, I'll just finish like this. Alright. Well, I think I've gone over most of the topics. Is there anything else that I should make sure to go over in particular?
Did you do sine and cosine?
So sine and cosine, the formulas are on the test. Do you want me to do a problem with them?
Like cosine is just like
Actually, I'll click
squared,
on
fourth,
that.
sixth, and then sine is just like third, fifth, seventh, ninth. That's basically it.
Yeah, he said that we could have those formulas on our test, I think.
Yeah, I think it gives it to us.
But as I was saying, use radians. Wait, Ryan, are
What
you
I
sending it
sent
to me?
in, what I sent in Math General is I think all that we're getting, and it's just the e to the x summation and then the cosine and sine x notation.
Yeah. I mean, it really helps with the power series, but it doesn't go over anything else.
The one that we don't get that you have to know is the natural log of a negative number, but that one's just really easy. It's just natural log of negative x equals natural log positive x plus I
Plus pi I. And if you actually put the natural log of a negative number in your calculator, while you're in the a plus bi form, it will just put that out. Although it has pi as a decimal, which is kind of annoying. But yeah, for example, if you have ln negative 2, as Ryan is saying, this is going to be ln 2. Oh my gosh, it's being kind of annoying. Equals, or ln 2 plus pi I. As a reminder, ln is what we use for e to the x equals negative 2. So here, if we add this for solving for x, we get this and then this. So that's the natural log stuff. I think most of that is fairly straightforward. But you can try that on your calculator quick again. Negative 2. It gives you the plus pi I. Alright. Do we have another thing that we want to go over in particular?
What is example 4? Write a complex number in exponential form.
Can you send it to me?
I can send you a picture, yeah. It's like the example.
Can you describe?
It's not that difficult. It's just the only form you need to know is a plus bi equals r e to the I theta, and then you can just use the r equals square root of a squared plus b squared, and then theta equals inverse tan of b over a plus pi, for when a is less than 0.
I have no clue what you just said.
Okay,
I'll send a screenshot.
let me describe it real quick for you too. Essentially converting to rectangular versus to polar form when you have imaginary numbers using Euler's number. So you'll basically find the magnitude, that's the r, and the direction, that's theta, and you just put it into this. So let's say we had a 3 at like 3 pi over 4. Just write it like this. I think there actually is. Yeah, there is an re to the theta I function on your calculator. I don't know what it does, but if you forget this equation during your test, if you go into mode and see the things by real, there is a plus bi and re to the theta I, so that will just remind you what it is. And maybe it's useful. I don't really know how it works. Wait, I'm gonna test it real quick to see if I go into it and then plug in an a plus bi. Oh yeah, it will just do the conversion for you. So if you go into mode and you go to r e to the theta I, and then you put in your a plus bi, it will do the conversion for you. So that's pretty helpful, I think. All right, anything more we want to go over?
Wait, how do you put this in again?
Go into mode on your calculator next
Yeah.
to real.
Yeah, I understand how to get into that mode, but how do I put in the complex number? Kind of forgot.
How do you put in a plus bi?
Yeah.
We'll just put in 3, like for example 3 plus 4, and then second, the second period.
All right. Thank you.
Alright, I'll zoom out a little bit so you can see all the things we've gone over. Alright, I might cut the recording in a second if there's nothing else we want to go over. But I think this is pretty good. So thank you all for coming. Let's stop recording here.